Welcome to part 2 of my testing of high voltages on high performance stepper motors for your 3D printer. In part 1 of this video, I used 0.9 Kraken V1s 3004 MAC stepper motors for my test. I got a number of people posting feedback that on average most people don't use 0.9 degree stepper motors and instead use 1.8s. So I decided to run this round of tests with the 1.8 V2 Krakens. Physically, the motors look very similar. This is actually a V1. It's a 0.9 stepper. Here is the new V2. As the previous version, it comes in this super nice box, storage container, and we open it up, and as I stated, it sure looks awfully similar. Just like the V1 motors, in addition to the standard stepper motor wires, you do have an extra pair of wires so you can take temperature measurements from inside the motor. One key difference here is the previous version had this socket where you could plug and unplug the cable, whereas the new version, the wires are permanently attached. But other than that, these motors look the same. And of course here you can probably see the model numbers as well. Looking at the LDO documentation for the torque curves, for the 0.9 V1 stepper, here you can see it starts off right around 600, jumps up to about 700 rather quickly, and then falls off from there. Looking at the V1 1.8 degree Kraken stepper, here we can see it starts a little bit higher by about 100 compared to the 0.9. It does run a little bit longer, has a little more torque, but really rather quickly it's got all its power up front starting at about 700, almost makes it to 800, and then drops somewhat rapidly from there. Both these motors have lots and lots of low-end torque. Looking at the V2 motor of the 1.8 degree stepper, the chart first of all shows different voltages, which is kind of interesting. And here we can see the motor starts off at really the exact same torque, no matter 24, 48, or 60 volts. And it moves up somewhat close to about 700 on 24, although it keeps going all the way up to about 750 using 48 or 24 volts. And then it decays at a much lower rate. And if you take a look at the numbers, you see the power band, instead of the very beginning at the start of the motor, when it starts to turn, it shifts much more toward the middle, and we end up with a really broad range of power. It doesn't quite start with the power of the V1s, but it eventually actually surpasses it. And then as it starts to gradually decay, again, it never really drops that much. Looking at the technical specs of all three motors, the first real differences here, the insulation classes. They're B, which is 80 degrees Celsius maximum running temperature for the V1s. The class jumps all the way up to H, which means 180 degrees Celsius. Now, on my printer, there's no way I'm running at that speed because it would melt the motor mounts. And so I plan on keeping it way below that, which probably means lower power. The resistance is roughly about the same across all three. But then when we take a look at the inductance, there's a huge difference. 3.5 for the 0.9, 2.3 for the 1.8 V1s, but it drops down to 1.6 for the V2s. And so that's 75% higher for the 0.9 V1s and 36% higher for the V1's 1.8 compared to the V2 motors. And so what does that mean? Typically with stepper motors, when we see higher inductance, we see increased low-end torque, but more heat, more vibration. When we see lower inductance, we see increased high-end torque, less heat, less vibration. Again, taking a look at this, we can expect the V2 motors should run cooler. In addition, the V2 motors should not have quite as much starting torque, but once they get moving, they should have quite a bit power. And we're about to find out if that's true. Stepper motors are not really super fast DC motors. And so traditionally, people are using either a 16-tooth pulley or in this case, a 20-tooth pulley. And here, just for comparison, I'm showing a 25-tooth pulley, which is really what I probably would have wanted to use. I also had these 30-tooth pulleys from the V1 motors that came with the motors. The V2 motors don't come with these anymore. Also notice that 30-tooth pulley is really designed for 9mm belts. On a standard Voron, the 30-tooth pulley won't work because the AB mounts won't support it, and this one in particular is designed for much wider belts, which won't fit because of that as well. The 25-tooth pulleys don't fit into the standard AB mounts either. 20 is the maximum size. That said, I decided to go with 30, and which meant, again, with 6mm belts, I need all new AB motor mounts. And it just so happens Mammoth 3D has these posted on printables, and these are explicitly designed for the Voron 2.4 and I believe the Trident as well, and it can accommodate 30-tooth pulleys just so long as they're designed for the standard 6mm belt height, which means the 30-tooth pulleys, the red ones I had from the V1 motors, are too tall. They won't fit either. So I ended up purchasing, and I've got a link in the description of this video, but I purchased 30-tooth pulleys that are designed for 6mm belts, and they work with these AB motor mounts from Mammoth 3D. You simply print these. You take the parts out of the old one, put them in the new one. You may need a few additional pieces that are listed on the BOM for this. Also, keep in mind that this is double shear, and so this means you also have to purchase a set of bearings that get inserted that allow you to increase your belt tension above the recommended levels. So one of my concerns with going with a 30-tooth pulley is what impact is that going to have on accuracy in terms of positioning the print head with the 3D printer. I ended up going ahead and creating a spreadsheet that represents the different pulley sizes in terms of teeth to help understand what the impact will be in terms of motion and accuracy as it relates to the printer, thinking that we tend to design at 0.1 millimeter resolution. This first section represents what happens when we don't use microstepping at all. And here I've laid out the 16-tooth, the 20-tooth, 25-tooth, and 30-tooth pulleys. I'm using, or at least basing these calculations on standard belts with a 2mm tooth spacing, which is, as far as I can tell, what almost every 3D printer uses. And then simply taking the number of teeth, multiplying it by 2 for 2mm is what our rotation distance is in millimeters. If we assume 200 steps per revolution, which is what our standard motor operates at, the distance that is traveled with a single step is listed here in millimeters. So with a 16-tooth pulley, 0.16, with a 20-tooth pulley, 0.2, 0.25, and 0.3. In terms of the number of steps to move 1 millimeter, with a 16-tooth pulley, we need 6.25, 25, 25-tooth pulley, 4, and then with a 30-tooth pulley, 3.33. Just for kicks, if we're looking at a 0.9 stepper, which has 400 steps per revolution on a 16-tooth pulley, that's 0.08 millimeters per step, or 0.1 millimeter per step on a 20-tooth pulley. I'd like to believe that means with a 20-tooth pulley or a 16-tooth pulley with a 0.9 degree stepper, you may not need microstepping at all. which is nice because that could resolve some of the torque issues because 0.9 degree stepper motors tend to have lower torque. I don't know if it's true. I haven't really tested this yet, although I will at some point in the future. The calculations, if we're using 16 microsteps, get really interesting here. Again, I've got the four different sizes of pulleys. The rotation distance is exactly the same. Nothing changes here. However, the distance per step is very different now. At 16 microsteps, a 16-tooth pulley will move 0.01 millimeters. At 20 tooth, it's 0.013, 0.016 for a 25 tooth, and 0.019 or almost zero point zero 0.02. The reality is here at 16 microsteps, really we should be able to print most everything. Based on how we typically design things, or at least how I think we typically design things. I'm a little bit worried about on a 30 tooth pulley that to move 1 millimeter, it's got to move 53.33 steps. I don't know where that 0.33 comes from, so I'm a little bit unsure about the accuracy. When we take a look at 400 step per rotation or zero point 0.9 degree steppers, the numbers really get quite fine here. With a 16 tooth pulley, each step is 0.005 of a millimeter, or 200 steps to move a millimeter, which is interesting. And, heading all the way up to 25, no problem. Again, I've got that 53.33, which, at least in my mind, bothers me a little bit. And when I look at the number of steps it takes to go per millimeter, we're looking at 106.667. I'm not sure how that works, but this is also why I'm working with a 30 tooth pulley. Just I'm interested. I know other people are using it, and I want to see what the prints come out looking like. If we go to 32 steps, 32 microsteps, again, looking at the same sizes with the same rotation difference, a 16 tooth pulley, we're looking at 0.005 millimeters per step. And again, these are pretty small numbers, and I think they're all, we should be able to print whatever we need to with this kind of resolution. The number of steps per millimeter, is quite a lot here. At 16, it's 200, although there we have 106.67 for the 30. And again, if we go to a 0.9 degree stepper, the numbers are pretty large here. Again, which means really a high level of detail we should be able to hit. Personally, once you get past 16, I have a hard time believing microstepping gets very accurate. So I'm not sure if, these accuracies can really be hit, but still, there's a lot here. Zooming back out to the entire chart as we take a look at these. Again, there's a couple of things that sort of jump out. It seems like 16 microsteps is probably all that we really would ever need. And at least with a 200 step per revolution stepper motor. And honestly, the same thing for 400 step per rotation stepper motor. The 400 step ones are really kind of interesting if we had a 20 tooth, because that means without microstepping at all, we should be able to get to 0.1 resolution, which for most prints is probably fine, but still 16 seems it to be it. 32, what's interesting there, with a 200 step per revolution motor, you're actually in theory hitting the resolution that you could with a 400 step per revolution at 16 microsteps. But again, I'm not a huge fan of 32 microsteps because 32 and above, I don't necessarily truly believe that we're really having or getting any type of real accuracy there, because I just don't see how a stepper motor can actually physically do that. But for those of you who know a lot more than me, please feel free to explain it in the comments. So now we get to the results of the actual tests. Here's an overview. I ran the tests at 2 amps, 1.5 amp, 1.25 amps, and 1 amps. The motors are definitely capable of 3 amps, but I don't have any kind of real or serious motor cooling. And so I could only run the tests for short periods of time at 2 amps before the motors started to get hot enough to actually melt my 3D printed AB motor mounts. And so this is what I did. I also tested these at accelerations of 25, 30, 40, 50, 75, and 100,000 acceleration. And I ran the tests unlike previously at, like previously at 60 volts, 48 volts, and 24 volts. I decided not to do 32 volts because previously I really didn't see much benefit to running the motors at 32 volts. The key difference here, I am running the tests at 4 different amperage values across all these different voltages. Running these motors at 2 amps, again, acceleration 25, 30, 40, 50K, 75K, and 100K at 60, 48, and 24 volts. The thing that really stands out here is at 2 amps, these motors are easily capable of accelerating up to 50,000 millimeters per second squared and being able to travel at 1,000 millimeters per second at 24 volts, 48 volts, and 60 volts. We can get up to 75,000 acceleration as well, and with very little penalty for 24 volts or 48 volts compared to 60 volts. And then at 100,000, again, at all 3 voltages, at 100,000 millimeters per second squared acceleration, the motors are equal. Now, at 2 amps, you will probably need something to cool the motors a little bit, but they definitely run cooler than the V1s. With a huge drop of half an amp, now running at 1.5 amps, again, running acceleration 25K all the way up to 100K, and at 60, 48, and 24 volts. We see at 25 and 30,000 millimeters per second squared, 24, 48, and 60 are all able to hit 1,000. At 40,000, 24 and 48 are able to hit 900, but we actually pay a penalty for running at 60 volts. And in fact, we see that penalty when we move up to 50,000 millimeters per second squared as well. That said, 75,000 acceleration, 24 and 48 are not capable of doing it. And at 60 volts, you can actually get all the way up to 100,000 millimeters per second square with a travel speed of 400. By the way, whenever my readings show 1,000, it's very possible that we could have driven further than 1,000 millimeters per second, but it was terrifying on my printer, so I stopped. Dropping down to 1.25 amps at 60 volt, 48 volt, and 24 volt at 25,000 acceleration, all 3 voltages are able to hit 1,000 millimeters per second. At 30,000 volts, there's a slight drop for at 30,000 acceleration. There's a slight drop at 24 volts, although 48 and 60 can hit 1,000. At 40,000, they're all equal. At 50,000 acceleration, they're all equal. At 75,000, 24 volts and 48 volts couldn't do it, but 60 volts could, but at 300,000. And I was not able to run these tests at any voltage at 1.25 amps at 100,000 acceleration. So now running at 1 amp, which is 1/3 the rated amperage of these motors, at 60 volt, 48 volt, and 24 volt, I was not able to break 40,000 millimeters per second squared acceleration. That was the upper limit. But still, all three voltages were equal at 25,000 and 30,000 acceleration. At 40,000 acceleration, again, we see we're paying a tiny bit of a price at 60 volts. And again, this is really kind of interesting. For pretty much any printer out there running 40,000 acceleration at these speeds, I think most of us would consider great performance. And these motors are able to pull it off at this low amperage at these voltages. Impressive. So zooming back out a bit at the whole chart, I think some of the things that really stand out here is with the V2 motors, 60 volts doesn't really get you much, and in fact, in multiple cases, it actually hurts. And so it feels like 48 volts is really probably the maximum voltage you ought to be working with on these motors. But the other thing that stands out is 24 volts, you don't really pay a price for that either. If you've wanted to upgrade to high performance motors, but you've been concerned about adding an additional power supply and the wiring related to it, I would say stick with your 24 volt power supply with these motors. And really, the key differentiating factor is the amperage. And 1 amp I'm actually running at. It runs fine. 1.25 amps easily handles any load I need to throw at it. And I'm actually personally not running these at 1.5 and above, which means the motors run really cool. And honestly, they're already capable of accelerations and speeds that my print head can't keep up. And really, I have resonance problems, at these high accelerations as well. So for all practical purposes, for most people, 24 volts, 1.25 amps is just fine. I don't know how many tool heads can actually keep up with 40,000 acceleration and 550 millimeters per second travel speeds. That's pretty awesome. So one of my worries with the 30-tooth pulley is how will an object actually print? As you remember, I had some issues with odd decimals, possible round-off errors, or things that we might encounter when printing at this speed. Now, please keep in mind, this is my first print after completely disassembling my gantry to get the motors in and make whatever changes I needed. Remember, I had to change and put all new AB mounts in here as well too. I also completely disassembled the print head, reassembled it. So, there may still be some other issues here that need to be taken care of. But again, how did this look and how accurate did it print? Well, let's take a look. So I'm trying to show this off in the worst possible light to show as many issues that I might be facing here. And here I can see a little bit of ringing, and after the Voron logo, there's a bit of an interesting pattern there. I'm not exactly sure what that is yet. I still have a little tuning. Here in this corner, or that edge, there's a little bit of a problem as well. It may be cooling. I could work a little bit on my surface layer as well. There might be a little over extrusion. And as you can see, based on the white on the bottom, I probably pulled it off the bed when it was too hot. But I'm curious about accuracy here. So 40.07, I think, is probably about as good as I could expect. Oops, let me check that again. 40.03 again. I think that's good. Maybe you can use, well, a little bit of adjustment there, but again, that's about 0.05 millimeter of an under, which again, I I think is probably really good. And so accuracy doesn't seem to be a big problem. And just checking this again. Not sure why I'm getting to slightly different readings here. Part of it could be the Voron cube is cooling down. Again, I pulled it off the bed when it was hot. I was a little bit anxious. Um, but again, either case, this is, I think, quite good in terms of accuracy. If you disagree, please let me know in the comments. Actually, any questions you might have, please add to the comments below. If you need anything, any tips, or if you have some thoughts on how to improve the quality of this cube, please add those comments as well. I'll include all links, and if you found this video informative, please click subscribe. And thank you very much.